Hello friends, in continuation to our previous classes, today we are going to discuss one of the important topic about gluconeogenesis. No? Gluconeogenesis. So far we have discussed about different carbohydrate metabolic pathways. Say for example glycogen metabolic pathway, say glycogenolysis, glycogenesis and others say hexose monophosphate shunt. In today's tutorial we will learn about gluconeogenesis. Okay. What is gluconeogenesis? Understanding the technical term is most important for conceptual clarity. Gluco with respect to glucose. Genesis means with respect to synthesis. Neo with respect to non-carbohydrate sources. Non-carbohydrate sources. New, it is with regard to non-carbohydrate sources. Say, combine these three words. Synthesis of glucose from non-carbohydrate sources is the technical meaning of, that means etymology of gluconeogenesis. What are those non-carbohydrate sources? Say, the major precursors or substrates for gluconeogenesis are pyruvate, lactate, propionate, glycerol and glucogenic amino acids. This is not an exhaustive list, but these are the most important precursors for the synthesis of glucose, what we call gluconeogenesis. Say for instance, pyruvate, lactate, propionate, glycerol and glucogenic amino acids. Glucogenic amino acids. These are all different non-carbohydrate sources which synthesize glucose. Then the next question, where does this happen? For example, gluconeogenesis mostly takes place in the cytosol of the cell, but some of the precursors may also synthesize in the mitochondria. And liver is the most important dish. That means origin, it's like place of occurrence. Liver is a place or organ where the gluconeogenesis takes place. That means most of the part. To some extent, kidney matrix also will undergo gluconeogenesis. But the thing is, liver is most important. At the rate of 1 kg of glucose per day will be synthesized in liver. With respect to kidney matrix, 1/10 of liver efficiency is reported from the kidney matrix. Then the next question, the importance of glucose we have to discuss about now. Glucose is the most important source of energy for brain, central nervous system, erythrocytes and testes. For example, out of 160 grams of glucose that a human body consumes per day, 120 grams of glucose will be consumed by brain itself. That shows the importance of what we call a line share of brain with respect to glucose utilization. And with regard to gluconeogenesis, it is the most important metabolic pathway. Say if a person is fasting more than a day, the basal requirement for the glucose is coming from this gluconeogenesis only. At the same time, some of the tissues, they accumulate, that means they produce certain metabolites like lactate, propionate, glycerol, which in turn goes to the blood, and this has to be filtered out. How? The gluconeogenesis will remove what we call filter the blood with respect to these metabolites. That means on the whole, gluconeogenesis is an important source of glucose for day-to-day life activities. Wherein these are the important non-carbohydrate sources. Okay, it is with regard to the basics. And in today's tutorial, we will discuss about pyruvate. That means synthesis of glucose from pyruvate and the lactate. The rest of the pathways, if you understand these two, it is easy to understand and go through the rest of the things. First, pyruvate. Gluconeogenesis coming from pyruvate. Before we go into the topic, we have to learn about certain basics of gluconeogenesis. In general, the reactions of gluconeogenesis are almost similar to that of glycolysis. Not exactly the same, but the reversal of glycolysis is in close resemblance to that of the gluconeogenesis. Reversal of glycolysis resemblance to that of close resemblance to that of gluconeogenesis. In the sense, say out of 10 reactions, 7 reactions are reversible, whereas 3 are irreversible. And these are common in both glycolysis and gluconeogenesis. This is a very important point. In glycolysis, if you go through the glycolysis pathway, there are totally 10 reactions, out of which 7 reactions are considered as the reversible reaction, whereas 3 reactions are considered as irreversible reactions. Say for instance, hexokinase and glucokinase. Say hexokinase in case of muscle, glucokinase in case of liver, which converts glucose to glucose 6-phosphate. It is number 1. It is the first irreversible reaction. Number 2, phosphofructokinase, which converts fructose 6-phosphate to fructose 1,6-bisphosphate. And number 3, pyruvate kinase, which converts phosphoenol pyruvate to pyruvate. These 3 reactions in glycolysis are totally irreversible reactions. We cannot, there is no similarity between gluconeogenesis with that of glycolysis with respect to these 3 irreversible reactions. And the rest of the 7 reversible reactions, there is complete similarity between glycolysis and gluconeogenesis. That means if we understand glycolysis, it is easy to understand gluconeogenesis. The only thing is the reversal of glycolysis. That's it. Say for instance, say pyruvate, then phosphoenol pyruvate, then the 2-phosphoglycerate, then the 3-phosphoglycerate, 1,3-base phosphoglycerate, glycerate 3-phosphate, then dihydroxysteroid phosphate, what we call phosphotriisomerase, then fructose 1,6-bisphosphate, then fructose 6-phosphate, then glucose 6-phosphate and glucose. Just in reversal of glycolysis, except these 3 reversible reactions which I have discussed about, say the reaction made by the hexokinase, the phosphofructokinase and the pyruvate kinase. And what exactly? That means how the gluconeogenesis will undertake these 3 steps. It will bypass these 3 irreversible reactions by alternate enzymatic machinery. That is how the issue ends. Except these 3, there is much similarity between gluconeogenesis in glycolysis, but in reversal of glycolysis. Today we are going to learn about these 3 important reactions. The rest of the same, just in reversal, so that we can understand better about how the pyruvate converts into glucose. Then, as we have discussed, most of the reversal of glycolysis is similar to that of gluconeogenesis. Okay, that means pyruvate conversion to glucose. Pyruvate conversion to glucose. Okay. We have discussed the 3 important reactions. Just focus on the first enzyme, first mode of reaction. Say, in general, the phosphoenol pyruvate. The phosphoenol pyruvate, what we call PEP, becomes pyruvate by pyruvate kinase. Here, one ATP will be liberated. It is in normal glycolysis. We knew that. Just the phosphoenol pyruvate PEP becomes pyruvate that means mediated catalyzing by pyruvate kinase, and here ATP will be liberated. One ATP will be synthesized. But in case of gluconeogenesis, this is not exactly the same. It's a different. We told you already. This pyruvate kinase, the third irreversible reaction in case of glycolysis, has to be bypassed by alternate enzyme machinery. How? Say, we'll take the example of gluconeogenesis. Just GNG means gluconeogenesis. Okay. In case of gluconeogenesis, this step, that means pyruvate should become phosphoryl pyruvate, not a single step but in two steps. First, the pyruvate becomes oxaloacetate by means of pyruvate carboxylase, which is a biotin dependent mitochondrial enzyme which has to rely upon the acetyl coenzyme A. And this pyruvate carboxylate converts, that means pyruvate, to oxaloacetate. And this thing actually happening in mitochondria. After the oxaloacetate forms, it has to transfer out of, that means diffuse out of the mitochondria into cytosol. We have discussed cytosol is a place where the most of the gluconeogenesis metabolic pathway will take place, though some of the precursors will also originate in the mitochondria. But the thing is, oxaloacetate is impermeable to mitochondrial membrane. It cannot diffuse out. So it has to transform into some other form. Say it through the enzyme malate dehydrogenase, the oxaloacetate becomes malate, and this malate easily comes out, that means diffuse out of the mitochondrial membrane into the cytosol. Actually, the enzyme malate dehydrogenase it's a reversible step. That means after it gets out, again it becomes oxaloacetate acetate, and this oxaloacetate subjecting the enzyme phosphoenol pyruvate carboxykinase becomes ultimately phosphoenol pyruvate. That means totally two steps in two different as parts of the cell. Half in mitochondria, other half in cytosol. We'll look how it ends. Okay, just imagine this is mitochondria. Just consider. Okay, this is mitochondria. This is matrix. Here, the pyruvate become oxaloacetate. Oxaloacetate. Oxaloacetate is one of the intermediate compound of Krebs cycle. We knew that. Krebs cycle. I'm not going to the deep. That means I'm not discussing about Krebs cycle. Just I'm representing. Okay. And this oxaloacetate will form coming through catalyzing by the enzyme pyruvate carboxylase. Pyruvate carboxylase. And here, actually pyruvate is a 3-carbon compound now. One CO2 has to be added and one ATP will be utilized here. So we got it. Oxaloacetate. But the thing is, this oxaloacetate cannot diffuse out of the mitochondria because it is impermeable. Sorry. And this oxaloacetate has to transform to some other form. Okay. Say malate. Catalyzed by the enzyme malate dehydrogenase. Okay. This oxaloacetate has to convert into malate, which is an irreversible step. How? Say, for instance, by oxidation. Here we will get one NADH. Okay. Then after this oxaloacetate, that means after we get the malate, it will come out of the mitochondria, and this is cytosol. I am repeating again. Oxaloacetate, which become malate through a reversible step made by the enzyme malate dehydrogenase, and this malate will come out of the mitochondria into cytosol. And after coming into the cytosol, this malate become oxaloacetate again by the same enzyme malate dehydrogenase. The same enzyme, malate dehydrogenase. Okay, we got it. Oxaloacetate. And this oxaloacetate will convert into phosphoenol pyruvate. How? By means of phosphoenol pyruvate carboxykinase. Here ATP is not utilized, GTP or ATP, that means not ATP. Say the GTP will be utilized here, and the carbon dioxide which we have fixed in the which is fixed by the carboxylase enzyme will be liberated here. That means oxaloacetate should become, which is a 4 carbon compound, should become phosphoenol pyruvate, which is a 3 carbon compound. So the issue, this is how the issue ends. Ultimately we get the phosphoenol pyruvate, but not in one step, but in two different parts, cytosol and the mitochondria. In general, in case of glycolysis, it is a single step. That means a irreversible step. Phosphoenol pyruvate here through pyruvate kinase become pyruvate. But in case of gluconeogenesis, this pyruvate in mitochondria first become oxaloacetate, which is one of the intermediate of the Krebs cycle, and this oxaloacetate, that means through the enzyme pyruvate carboxylase, and this pyruvate carboxylase is one of the important regulatory enzyme. One of the important regulatory enzyme for gluconeogenesis. This pyruvate carboxylase, which convert pyruvate to oxaloacetate simply by by 1 ATP and 1 carbon dioxide will be placed here. And this oxaloacetate, which is impermeable to mitochondrial membrane, will convert to malate by malate dehydrogenase, and this come out, that means cytosol become oxaloacetate, which is a reversible step. Then it become phosphoenol pyruvate by means of phosphoenol pyruvate carboxy kinase. Here 1 GTP, here no ATP should be utilized. 1 GTP utilized, and the carbon dioxide has been fixed by the carboxylase will be liberated. So we got it. That means phosphoenol pyruvate. The first irreversible step with respect to glycolysis has been sorted out. I told you how the alternate enzymatic machinery. This is how it is with respect to the first reaction. Then the second reaction, the second reaction is at fructose 1,6 bisphosphate. That means in case of glycolysis, the fructose 6-phosphate become fructose 1,6 bisphosphate by phosphofructokinase. And how this, even here with respect to gluconeogenesis, there is one enzyme called fructose 1,6 bisphosphatase, which converts fructose 1,6 bisphosphate to fructose 6-phosphate. This is a single step. No need of this complicated process like cytosol, mitochondria and intermediate compounds. Just a single step. Fructose 1,6 bisphosphatase will convert fructose 1,6 bisphosphate to fructose 6-phosphate. Second enzyme sorted out. Second irreversible enzyme. How about third? That means the hexokinase. Here there is another enzyme called glucose 6-phosphatase. Just a single step which converts glucose 6-phosphate to glucose. That's it. That is how the pyruvate becomes glucose. Okay. We will see how the issue ends. Okay. Then here we got it actually now. Phosphoenol pyruvate we got it. Here we got phosphoenol pyruvate. And this phosphoenol pyruvate may undergo, as it is as usual reaction with respect to glycolysis, but in reverse. First become 2-phosphoglycerate. Then becomes 3-phosphoglycerate. Then becomes 1,3-bisphosphoglycerate. 3-bisphosphoglycerate. Then becomes glyceraldehyde 3-phosphate. Glyceraldehyde 3-phosphate. Then we knew that dihydroxyacetone phosphate, DHAP. Then becomes fructose 1,6 bisphosphate. Up till fructose 1,6 bisphosphate, it is the same process. Okay, I'm not going to that means I'm not going to the enzymes which is responsible for this. Just imagine we have discussed about glycolysis. After you get the PEP, phosphoenol pyruvate, it goes in the reversal direction up till, that means until the fructose 1,6 bisphosphate. What happens next? In case of normal process, say the fructose 1,6 bisphosphate, how it forms? from fructose 6-phosphate. How? This is a irreversible step now. In case of normal glycolysis, I am saying, say one ATP will be utilized here by means of phosphofructokinase. But here, in case of gluconeogenesis, this fructose 1,6-bisphosphate become fructose 6-phosphate. Simply how? It has to remove the inorganic phosphate. Catalyzing by the enzyme, this is very important. Fructose 1,6-bisphosphatase. Bisphosphatase. The second irreversible step. Okay. Then we got fructose 6-phosphate. Then it become glucose 6-phosphate. Glucose 6-phosphate. This is glycolysis and this is gluconeogenesis. We got it. Then glucose 6-phosphate become glucose. That means in case of glycolysis, glucose become glucose 6-phosphate by hexokinase. In case of muscle, or glucokinase in case of liver. Here ATP will be utilized. Here in case of gluconeogenesis, gluconeogenesis, glucose 6-phosphate has to become glucose by means of an enzyme called glucose 6-phosphatase. 6-phosphatase. Simply by removing the inorganic phosphate. In case of gluconeogenesis, this is the first irreversible step. Okay, simple. After we get the PEP, until fructose 1,6-bisphosphate is common. Again, the second irreversible step. Say in case of glycolysis, now we have discussed fructose 6-phosphate become fructose 1,6-bisphosphate by phosphofructokinase, and here ATP will be utilized. In case of gluconeogenesis, this fructose 1,6-bisphosphate become fructose 6-phosphate by means of an enzyme fructose 1,6-bisphosphatase. That's the only difference. It's a single step reaction simply by making one phosphate group. Okay, that will be hydrolytic reaction. That's it. And after we forget the fructose 6-phosphate, the same again, glucose 6-phosphate, and this glucose 6-phosphate has to become glucose, the first most irreversible step. How? In case of glycolysis, this by means of hexokinase in case of muscle, or glucokinase in case of liver, and one ATP will be utilized here. In case of gluconeogenesis, the reverse, but the enzyme responsible here is glucose 6-phosphatase, which that means this is just like here hydrolytic reaction, removing the phosphate group, ultimately forming glucose. This is how the issue. This is the central dogma of pyruvate to glucose. This is how the issue ends. This is the most important reaction. Just remember 3 reactions. The 3 irreversible reactions you have to study. The rest is same. Only in irreversible direction. That's right. In reversible direction. The first most irreversible step, that means reaction is in case of glycolysis, hexokinase, phosphofructokinase, and pyruvate kinase. Focus on the pyruvate kinase. How the pyruvate become phosphoryl pyruvate in case of gluconeogenesis? The pyruvate should become oxalate state, and it has to become malate, come out of the mitochondria. Then the oxalate state become phosphoryl pyruvate. Then it starts the usual process up till fructose 1,6-bisphosphate. Then by means of glucose or fructose 1,6-bisphosphate is become fructose 6-phosphate, then glucose 6-phosphate, then glucose. Then how? Glucose by means of glucose 6-phosphatase. These are 3 enzymatic reactions. Okay, this is about how the pyruvate becomes glucose, the first important reaction of the pathway of gluconeogenesis. Then we look into the next phase, how the lactate, how the lactate becomes glucose. How the lactate becomes glucose. Lactate will be produced in active skeletal muscle. Actually lactate is considered as a dead end of glycolysis. Why? Because in case of anaerobic production, it will produce lactate. There is no further continuity of pathway. Therefore, it has to continue. That means it has to flow back to pyruvate so that it can continue the metabolic pathway. Here, the thing is, in case of skeletal muscle, though it is pyruvate or lactate, cannot become glucose. We have discussed in this in the pyruvate to glucose conversion how there are three different enzymes, say the glucose 6-phosphatase, fructose 1,6 bisphosphatase, and then pyruvate carboxylase and phosphoryl pyruvate carboxykinase. Here glucose 6-phosphatase, which converts glucose 6-phosphatase to glucose, and fructose 1,6 bisphosphatase, which converts fructose 1,6 bisphosphate to fructose 6-phosphate, are not present in skeletal muscle. That's the important point. In case of, just I will repeat again, in case of skeletal muscle, there are no enzymes which can convert the fructose 1,6 bisphosphate to fructose 6-phosphate, which is actually the duty of fructose 1,6 bisphosphatase, and also the glucose 6-phosphatase, which converts the glucose 6-phosphate to glucose. So what happens? Say the lactate which the skeletal muscle produce have to travel to the liver, because it I told you already, most of the gluconeogenesis takes place in liver because it has a sufficient enzymatic machinery, and this lactate through blood will have to reach the liver. Then in liver it oxidizes to pyruvate. That means pyruvate become lactate simply by reduction reaction catalyzed by the enzyme lactate dehydrogenase. It's reversible. The lactate become oxidized to pyruvate in liver, and this pyruvate again the same process, glucose 6-phosphate and glucose, and after forming glucose in liver, it has to flow back to the skeletal muscle through blood, what we call Cori cycle. You know how here lactate to glucose, what we call Cori cycle. How? Say for instance, these are the two organs are involved. So this is skeletal muscle and this is the liver. Just a rough sketch, okay? This is the liver. In case of skeletal muscle, after forming glucose, then glucose 6-phosphate, then pyruvate, then become lactate. And how pyruvate become lactate? By means of lactate dehydrogenase. And this lactate will try, this is blood, will enter the liver, and this lactate become pyruvate by oxidation, same by oxidation, what we call oxidation reaction. That means a lactate dehydrogenase, the same, because it is an irreversible, so it's a reversible reaction. Okay, then this pyruvate become glucose 6-phosphate, and this glucose 6-phosphate become glucose. Okay, this is a muscle. Okay, and after forming glucose, it will flow back, it will go back to the muscle. That means synthesis, what is Cori cycle and how lactate become glucose? The synthesis of glucose in liver from the lactate of active muscle, that means skeletal muscle, and the utilization of this glucose by the skeletal muscle which has been synthesized in liver is a Cori cycle. Why such a huge mechanism? All the way the muscle has to flow to the liver, through blood, and again conversion to glucose, and again coming back to glucose, that means skeletal muscle, for energy production. Why? Because it doesn't have two important enzymes, glucose 6-phosphatase, and fructose 1,6 bisphosphatase. Fructose 1,6 bisphosphatase. Because of lacking of these two enzymes, no, in skeletal muscle it has to depend on liver. This is how the issue ends. This is with respect to how the lactate become glucose. Regarding other precursors, say for instance glucogenic amino acids, say the carbon skeletal of all glucogenic amino acids except lysine and leucine will eventually become that be converted to pyruvate, or the intermediates of Krebs cycle which ultimately becomes glucose through the same mechanism. I told you already, if you understand the pyruvate to glucose, that means gluconeogenesis, and lactate to glucose gluconeogenesis, it is easy to understand. The only thing is, so what are you made with the precursor? Say it is glucogenic amino acid or a glycerol or a propionate. It has to transform, that means convert into one of the intermediaries, say for example one of the intermediate of Krebs cycle, or the product of glycolysis, say pyruvate, or the intermediate of glycolysis, say the dihydroxyestrogen phosphate. Through these channels, these become ultimately glucose, and ultimately after the energy. This is how the issue ends. Let us focus on one particular example regarding the energetics. Energetics. Say we have discussed about pyruvate now. With respect to pyruvate to glucose. How many ATPs are produced like that? Say 2 pyruvate, the reaction will be like this, plus 4 ATP plus 2 GTP plus 2 NADH plus 6 H2O, gives us to glucose plus 4 ADP plus 2 GDP plus 2 NAD plus 6H plus 6 PI, not going phosphate.